Hello students, welcome back. Previously we completed up to here. When we have a product of two residue class groups, we have two generators in general, 1, 0 and 0, 1. Now when can I reduce that into a single generator? For Z2 times Z2, no. For Z3 times Z3, no again. For Z2 times Z3, yes, this time. In general, it turns out that when M and N are relatively prime, yes, otherwise no. In this case, GCD of 2 and 2, that's 2, not 1. GCD of 3 and 3, that's 3, not 1. Now GCD of 2 and 3, that's 1. So we had no, no, yes. Of course, we have to prove it here. There are m elements here, n elements here. Cartesian product will give me m times n elements. So if this is cyclic, then it's going to be isomorphic to Z mn. And then that happens when the greatest common divisor is 1. When m and n are relatively prime. How are we going to prove it? We're going to use this kind of strategy. We'll pay particular attention to 1, 1. And then for arbitrary case, well, we're going to consider those later. 1, 1, that's going to be important. Okay, here we go. Let's pay particular attention to 1, 1. And how do you calculate its order? It turns out that the order of this particular element, 1, 1, is the least common multiple of m and n. That's my claim. So the order of this element, or more precisely speaking, the order of the cyclic subgroup generated by 1, 1, is of course the minimum, the smallest positive integer, such that that element repeated k times that group operation is the identity. Here we are using the addition notation because this is a abelian group, but previously in lesson 3 in cyclic groups we used to use power notation. A to the k power equals to e, that's what we used to use, but here k times a as a coefficient equals to 0. It's the same thing, just abelian case like this. And then of course we have to work out a little bit, and eventually that's what we want to prove. In any case, comfortable with this. So we used to have this kind of thing in general. But that's when we had repeated group operation in multiplication form. Here, repeated group operation is done in repeated addition form. So we write like this. And that's what you're looking at over here. So okay, let's do this computation. How does it work? K times 1 is k, so we have k bar is 0 bar 0 bar. All good? Consequently, k is congruent to 0 modulo m, and k is congruent to 0 modulo n. In other words, m divides k and n divides k. And smallest such k, what is it? It's the least common multiple. Just the definition of it, isn't it? And everybody must remember this, right? mn over GCD. So if GCD is 1, then the denominator is 1, so the order of this element is m times n, so we have a cyclic group. We're going to talk about that in more detail in step 3. Okay, alright, step 1 is done. Now how about step 2? The arbitrary case, a bar, b bar. And we'll prove that this is going to be less than or equal to the LCM. Same thing, k times this element is 0, 0, the identity, and we use similar computation. Ka bar is 0 bar, Kb bar is 0 bar, so K is equal to 0 modulo M, Kb is congruent to 0 modulo N, so M divides Ka and N divides Kb. So far so good. But A and B can be non-trivial and may take up some factors of M or factors of N. If it doesn't, then it's the same as the LCM, but otherwise it may become a little bit smaller. So what do we have? Arbitrary case order is less than or equal to the maximal case, which is 1, 1, and that's Mn over GCD. That's the LCM, so it's Mn over GCD. Maybe I should express one more time here. So here's the main proof. GCD is 1, that is, if we have relative prime, LCM is M times N. Yeah, denominator is 1, denominator is 1 there. Therefore, the order of 1, 1 is Mn. So 1, 1 generates everything. So this group here is a cyclic group, consequently isomorphic to ZMn. Now what if GCD is not 1? It's greater than 1. In that case, LCM is less than Mn, strictly less than Mn. Consequently, the 1, 1 case is the maximal case, right? Remember that? This 1, 1, order of 1, 1 is actually the maximum order. So maximum order is less than Mn, which means there's no element that's going to cover entire Mn. So when M and N are relatively prime, then cyclic. If they're not, then non-cyclic. That completes the proof. So a direct product of two residual class groups turns out to be cyclic if and only if M and N are relatively prime. Now what if we have more than two products? In that case, we just applied 2 at a time repeatedly, and we can conclude like this. Pairwise GCD is 1 for all pairs. Then we can reduce, and then we have n-1 products, and we can prove it recursively like that, or inductively. The detail is left to the students there. And let's go to further example problem. Oh, before that, I'll be more mention about least common multiple. Yes. The order of any n-tuple is equal to the least common multiple of each of those. Okay, all right. That's basically the repetition of what we did in a little bit more generalized version, just slightly more. Now let's go to an example problem. And this one, it's going to be really hard to do it right precisely. Let me give you a trick. We did something in lesson 4 when we did cyclic groups. I think that was lesson 4, wasn't it? If n is strictly greater than 0 but less than m, then the order of n in Zm is m over GCD of Mn. And let's see, the proof is, let's come back to the proof either as an optional video or I'll simply ask you to go back to lesson 4. In any case, remember that, and we're going to use it. Okay, how do you solve that? Well, 8 bar, 4 bar, 10 bar, those are basically n bars, where m value is 12, 60, and 24. So 8 bar has order m over GCD. So Z12, so 12 over GCD, which is 4, so order 3. How about 4 bar in Z60? It's m over GCD. GCD of 4 and 60 is 4, so we have order of 15. And 10 bar, 24, m over GCD. And then GCD of 10 and 24 is 2, so 24 over 2 is 12. This computation is not difficult at all. So we have all that. And then we are taking triple, right? So we'll simply take the LCM. And the LCM of 3, 15, and 12 will turn out to be 60. If we want to calculate all those in this group, it's going to be an ordeal. Especially things like Z60 or Z24, it's going to be really hard to calculate because numbers are so big. But if you use this lemma, then you can find out the order of each component. And then just take the LCM and that's it. Now, as for the proof of this lemma, no, I take it back. I'm not going to even do it as an optional video. We did it already in lesson 4, theorem 4.3. So I'll simply ask you to revert back and review lesson 4. Just remember the result. And this is going to be very, very useful in these kind of computation problems. Okay, all right. So much for section 1 of this notebook.